There's 60 minutes allocated or 50 minutes?
50 minutes plus questions.
Okay, you're all set, Dr.
Okay, thank you. All right. Welcome, everybody, to the multidisciplinary seminar in ECE. And it's a pleasure to have here Professor Peterson. Professor Peterson received a BS in physics and MS and PhD in mathematics from Carnegie Mellon. And he's written a well-known book in geometric programming, which was translated in several languages. He's an author of many papers, many research papers. He's been at the University of Michigan, Northwest, and NC State, from which he retired in 2004. He is currently at the U.S. Army Research Office, where he's leading the program on complex systems. And it's a pleasure to have you. Thank you for coming. The floor is yours.
And let me begin by thanking Professor Krim for inviting me to give this talk. And it's good to see some old friends in the audience. And also, let me say that please feel free to interrupt me at any time, make a comment, ask a question, or whatever. So what I'm going to be talking about, at least initially, is solving a linear system of equations, coefficient matrix capital A, and it is m by n, and the column vector on the right-hand side is, of course, an m-dimensional vector, and then the unknown, I'm using the symbol chi instead of the normal symbol x. And the reason for that is I want to keep x in the background to use it in a different way. And so let's imagine we're looking for a column vector chi.
I forgot to tell you,
it's
better to use a pen because your finger will move the
I see.
will move ahead the slides.
I need to go
Just
back.
Go back, yeah. There you go. And you can erase that, by the way, too.
Oh.
You have to put the pen down. Put the pen.
Did I just put that on there?
I think I did it, but for some reason it's not.
It didn't show up to begin with.
I don't know why.
Reverse
it. All right.
Well, we'll just read it there. I think it's still readable. There are several ways of going about this. Of course, the classical way is to use Gaussian pivoting on that augmented matrix, and that's known to, you can do that with a finite number of pivots, and in exact arithmetic, if you can do that, you can't on a normal computer. It's cubic computational complexity, meaning, of course, that the amount of computational effort goes up with the amount of data that goes in a cubic way. And one disadvantage to that is that once you get large systems and you have to terminate early because you simply can't get it through, if you terminate, there's typically no usable approximate solution for that. So you've wasted your time. And so over the years, people have tried to solve large-scale systems in a different way. And probably the earliest effort was in the early 1950s by Hestenes, Lanchos, and Stiefel, so-called conjugate gradient method. Incidentally, some of you may know this, but I didn't know until recently. When they published that in the early 50s, it looked nice theoretically, but people claimed it didn't work in practice. And it was totally ignored for something like 20, 25, 30 years. And then in the 70s, people discovered how to overcome that. And now I think it is the way of solving large-scale linear systems. But it does require that m be equal to n, so we have a square matrix A, and not only asymmetric, but also positive definite, which is not a serious restriction for many problems from the physical sciences, but still for some it is. And essentially the way that works is you minimize this quadratic function. There's the quadratic part there. The capital T, of course, means transpose. And if you have a square matrix A and it's symmetric, then when you take the gradient of that and set it equal to 0, the gradient just comes down to being, it's just A chi minus that B. And so the optimal X satisfies that necessary and sufficient condition. And of course, this is the same as that, and so you have a solution. And the important thing about this is that you only really need n conjugate gradient steps, and if you can do exact arithmetic, you have the exact solution. Of course, typically you can't do the exact arithmetic. There's round-off error, and in that case, whether or not how quickly it converges comes up, and it converges superlinearly. And most importantly, unlike the Gaussian methodology, if you stop at some point, you typically have an approximate solution that's usable. You can see how much error is involved in that solution. You just simply look at what the gradient is where you stop. You're trying to drive the gradient to 0, and you see how far the gradient is from 0, and that tells you essentially what the residuals are. So what I hope to do is provide alternative methods to this, and they will be dual-based methods. That means we'll have functions we want to minimize, but it will not involve the vector variable chi, at least not directly. It'll be over on the dual side, and instead of trying to drive the gradient of some objective function to 0, the gradient will turn out to actually be the solution chi. And so that's why it's called a dual approach, okay? So let's see how this goes. Okay, here's the generalized geometric programming methodology. Important thing here to note is that in the other methodology, the Gaussian methodology, and to some extent also the conjugate gradient methodology, you talk about an augmented matrix like that, or a partitioned matrix, and you have a plus b there, plus b. I'm going to put a minus b there, and it's because we're going to focus not on that particular representation of the problem, but on this representation, obviously equivalent. And to work with geometric programming, those of you who know it, and at least one here is as much an expert as I am, to work with that you need either a pair of orthogonal complementary vector spaces, or more generally a pair of dual closed convex cones. And since we're just dealing with equations at the moment, we'll be able to get away with the simpler concept of just orthogonal complementary vector spaces. But if you look at this, you say, where's there an orthogonal complementary vector space? I don't see it. Vector space is a solution set for a linear system that's homogeneous, right? So I have to make that into something that looks homogeneous. It's starting to look homogeneous here, okay? So those zeros on the right-hand side. Now, in order to go further to get a vector space out of this, we simply look at the null space of that matrix, okay? And remember what the null space is. Here I'll call it capital X. It's all those vectors lowercase x such that that matrix times the column vector x is 0, okay? So we have that. And now the orthogonal complement of that vector space, capital X, is just the row space of this matrix. And that row space I'm calling capital Y. So what is the row space? It's all linear combinations of those rows. And to take a linear combination of those, an arbitrary one, I need to bring in another vector variable z. Incidentally, all variables here without a capital T on are column vectors. So if I put a T on, it's treated as a row vector. So we take the row vector z super t, multiply it into that matrix on the left, and we're automatically taking a linear combination of the rows of that partition matrix. And so z varies over all of Rm. And the vector y then traces out all points in that space.
So you're assuming A is a full rank.
Oh, no assumptions about, no requirement on A. That's one good thing about this, absolutely.
So the null space can be more than one dimension.
It can be any number of dimensions. That's right. And I'm glad you asked that question, because I should have mentioned that here. Unlike the conjugate gradient method where you have to make all kinds of assumptions about it, you don't make any assumptions about A here. Okay, so now these two vector spaces, hopefully you all remember from a linear algebra course that they are orthogonal complementary vector spaces. So now we're sort of in a generalized geometric programming format. Incidentally, some of you who may know about geometric programming originally back in the 60s, what I now call prototype geometric programming, these vector spaces are, one vector space is the column space of an exponent matrix, and the other is the orthogonal complement of that. Okay, and so that's why this orthogonal complementarity plays a key role, and this is just a completely different setting for it, but abstractly it's within that branch of mathematics. So we do that, and the first thing I want to observe is that if we have a vector x in this null space, how does that get us a solution chi back here? It gets a solution chi if we know that the n plus first component of x is not 0. Because if it is not 0, remember what this is saying. It's simply saying that if I I need to go back. Yeah, I better not get too close.
You can point with a pen.
Oh, a pen. Okay, I'll use this one. So here's the picture you need to have in your mind is think of that vector x really as a row. We're taking your inner product of x with each row of A minus B, and we have it equal to 0. And so if the n plus first component of such an x, that's the one that's multiplying numbers in this special column here, is not 0, we can divide through each of those equations by that non-zero number. And then the result, the first n components, would be a chi. Is that clear? Because you then have a 1 multiplying this here. So you have inner product of the first n components with each row of A plus 1 times a minus B equal to 0, transpose, you got it. Okay? So that's the key relationship here. If we can get a solution to that, a point in this vector space where the n plus first component of x is not 0, we've got a solution to that problem. Okay? And what we're going to see is that in a sense it's easier to do that by working over here in this vector space y, because here we're just taking linear combinations of the rows there, and we're going to construct optimization-like problems, some of which are actually optimization problems, where we're going to minimize some function of y over this particular row space, and essentially that's unconstrained. It may have constraints if the domain of the function, we're going to call it h, we take, does not have a domain that's all of Rn plus 1, but it need not have any constraints. And so if we take such a function, an appropriate type of function, and minimize it, much like you would do in the conjugate gradient methodology, except you're doing it on the chi side. If you minimize it, then you're going to come out with a chi also. That's going to be the duality theory of geometric programming will tell us how to do that. Okay? So that's the key idea here. And now the next, okay. This is more or less what I just said. Each vector x in that null space with a non-zero component x sub n plus 1 provides a solution that we're after. And so we simply use the first n components of the vector xo for xn plus 1 in the definition of a primal geometric programming problem. Row space y is used in a definition of a corresponding dual geometric programming problem. And let me draw a little picture up here to motivate what comes next, at least what I think comes next. This is a little different from the original version, but this will help explain what's coming. Let's see, is this a pen?
Yeah, you can write with that.
I'm going to put this over here. I'm going to do a two-dimensional case. So I mean these lines to be orthogonal, and I'm going to call this is going to represent that row space y. And of course that's the origin right there, say. And this will represent the null space capital X, and so they're perpendicular. And now what we're going to do is we're going to take and define a function for the dual problem. That's going to be so a function has a domain. In these slides, that domain is called D. So I'll just put one here. It might look something like that. So that's going to be called D. Now, in these optimization problems, where they could be equilibrium problems, could be like finding saddle points or something, that'll work just as well. We want to take and intersect the domain of the function that we're dealing with, and that function can be almost anything, unlike the conjugate gradient method where you have to have a quadratic function. It can be almost anything, as we'll see. So we want to take the intersect of the domain of that function, whatever it is, with y. That's going to be our feasible solution set. So in this picture, that's that set there. And we're going to minimize over that, or we're going to more generally look for critical points. Now, in this diagram here, this would be a critical point right here if and only if the gradient, let's assume for the moment we're dealing with differentiable functions h. So h is a differentiable function with domain D. And it's got to be that the gradient at a critical point has to be orthogonal to y. Isn't that right? So I'm going to put here, this would be the gradient of a given function h. You give me any function you like, and we're doing it at yCr. CR is critical. And in particular, if that's an optimal point, either minimizes or maximizes h, let's say it minimizes h just to be specific, this has to be perpendicular to that, because if it was that way, you could get h even smaller by going in the opposite direction, right? So it's got to be like that. So that's, I wanted to show you that to you graphically, but it's true in any number of dimensions. And probably on the next slide here, we will see this. The notation here gets a little bit messy, and that's why I wanted that picture in mind. So we're going to deal with a dual geometric programming problem. I'm going to give it the symbol Q, because we're working with y instead of x. When we eventually work with x again, we'll call that the primal geometric programming problem. That'll involve that null space, and we'll call that problem P. So there'll be ultimately two problems, primal problem P that I haven't thoroughly described yet, and a dual problem Q. And since we're doing dual variational principles, it's more important to be on the dual side, and that's why that problem Q is coming in here first. But to make this more precise, we have a domain of a function here. It's a composite function, and we're dealing with this vector z. Remember, z, the components of z are the coefficients in the linear combination of the rows of that augmented matrix. So z belongs to Rm. It's transposed times that partitioned matrix gives a y, a vector y. That keeps us in the vector space capital Y. So in that, we want that to be in D. That's simply saying not only are we in Y here, but we're in D, so we're somewhere along here. And then we're going to say, suppose that we are in the interior of D. That's the way I've drawn it, so that the gradient exists there. You can't be on the boundary. Typically, D will be the whole vector space anyway. And so you can differentiate it there. And so we want to find critical points for that. Okay, so we take that function, h with domain D, and if we know it's convex, we're going to minimize it because they will presumably be the only critical points. If it were if it were concave, you'd maximize it, or you might just want to take minus that and minimize it, so we can always talk just about minimization. Or if it's neither convex nor concave, you could look for saddle points. The important thing is, say you're looking for where this happens here, the gradient of h at a point where y intersects D is perpendicular to y. It has to be, right, or it's not a critical point. Notice, though, when that's true, this is parallel to this, so that vector is back in x. That's where we want to get it, right? We want to get it back in x, because remember, it's a vector in x whose last component, whose n plus first component, if it's not 0, we immediately have a solution to the original problem. That's the key idea here, okay? It's the key idea. And doing something with a function along here, that's unconstrained. Unless there are constraints because enforced by the boundary of that domain D. And maybe sometimes one would want to do that. Maybe you want D to be, in this case, all of R2. In the general case, all of Rn plus 1. Okay, so that's the key idea here. All right. Now, that more or less explains what's going to come here. Observation. If Q has a critical solution, it would be ZCR here, but the ZCR would be mapped into the YCR, because remember, Y is a linear combination of the rows of that special matrix with the Z, the components of Z multiplying those rows. But the important thing is the image of the Z critical, which is the Y critical, which puts you in there, and then we have this. You can give a precise proof that that has to be an X simply with the chain rule, okay? And it's in somewhere in here, I think, but I don't want to go into that kind of thing. Okay. If Q has critical solution Z critical such that its image Y critical, that way, is an interior point of D, I've drawn it that way here, at which H is differentiable, then by the chain rule we have that important relationship here. This is just saying that that particular vector is it's perpendicular to Y, and so it's in X. Because they're orthogonal complementary spaces. And so if that vector gradient of h at that critical point y critical has a non-zero n plus first component, then the first n components of that provide a solution chi that we're looking for. It's that simple.
When do we know that the Q has a critical point in D, in the interior of D?
Well, if it
Efficiency, existing condition.
you're getting, if you'll delay for another
Okay.
20 minutes, we'll get to. That's going to, I'm going to bring in the general duality theory of
Right.
geometric programming. It'll bring in existence
Right.
questions. That's a good question, and I'll try to answer
Because
that.
everything hinged upon that.
Everything hinges on that. That's right. Right. But given that there is this, and you happen to get one where that n plus first component is not zero, you've solved at least you have one solution to the original problem. If there's more than one, there might be others. But this says that if you do this and that happens, you've got a solution. And you might use Hessene's, Lancho, Stiefel kinds of methodology or something on it, okay? But there's complete flexibility here, and that's why I mentioned in the abstract, there's infinite flexibility here on how, the only thing that's fixed for you is this pair of orthogonal complementary vector spaces, but you can take this presumably H function whose domain D, almost anything, but there will be certain kinds of functions that will be most important. Okay. So, that's the same thing, isn't it? Now, this is just a comment that we could get even more general, that we can replace the differentiability assumption. Incidentally, this notation here, H D, simply stands for a function. Since you don't see an arrow to the right pointing to the real number system symbol, it means it's a real valued function. And D is the domain of the function, and then H represents it. So in this case, you would write H of Y, and Y would be in D. And of course, a critical solution must be in D. We could replace that with a generalized differentiability assumption using Clark's work in non-smooth analysis, but I don't want to get into that. I mean, someday that might be useful, but for the moment, I mean, at least we have a lot more flexibility than the conjugate gradient people had. And why push it to its limits? Maybe this is all we need, right? If I talked about that, we would get into real complicated analyses, and I don't want to do that. Okay. Now, to guarantee the secondary assumption, namely, what is it? It's that the n plus first component of the gradient of h at the critical point is not zero. That is, of course, this notation. H sub n plus 1 is just the n plus first partial derivative of h. It's the standard notation. So we don't want that to be zero, because if it is zero, then we can't divide through by it and hence get a solution chi to the system we're originally after. So we want to maybe narrow our choice of functions h so that is automatically satisfied. And that's what I'm going to do next. And to do that, there would be other ways of doing this, but this is the way I like best at the moment. We take a function that's in partially separable form. That means the function is the sum of at least two functions, and one of the two is in a domain that's independent of the domain of the second function. That's what we mean by partial separability. Complete separability of the function hd would simply say that h is a sum of terms, in this case n plus 1 terms. Each term depends on only one component of the vector y, and each of those components of y are restricted into separate intervals. Okay, those are the simplest kind of nonlinear function you can deal with. So we're going to go partially in the following way. We're going to take and let, here's a little problem here. These two symbols are different. in what I had written, this would not be bold and that would be bold. But I hope this doesn't make too much confusion. But we've taken the original domain D and we've written it as a Cartesian product of a domain bold D with just a real line. And we do that in such a way that y1 through yn is equal to, this is going to blow me away, I'm afraid. I can sort of see the difference between those two y's.
Yes, there is some difference.
Okay. The new HD is bold. The original one was not bold. And so this is the original one, and that's the bold one. And the bold one only depends on the first n components of y. And then there's a very special function for the n plus first component. It's the simplest kind of non-constant function you can get, just y sub n plus 1. Okay, so we do that. Now, why do we do that? Well, it's because if we work with functions of that type, and we still have complete arbitrary functions here, and now that this, incidentally, that bold y is back in Rn, where we sort of know our solution chi is going to be anyway. But if I take the n plus first partial derivative of this, that's simply the derivative of y sub n plus 1. That's 1. 1 is never 0. And also, when we're eventually dividing through by that n plus first derivative, we're dividing through by 1. It doesn't do anything. Okay? So this helps that way. So since that n plus first partial derivative is 1, we are guaranteed that that is not 0, and the solution chi to that is simply the first n components of that, and this is just 1, so it's just this here. It's just the gradient, really, of that part right there. That's the solution to the problem. Okay. So for the rest of the talk, we'll restrict ourselves to that case where we're only dealing with functions h where the dependence on y sub n plus 1 is only that way. Now here's an example. We could choose that bold D to be all of Rn. Let's see, this is not bold. Bold D here, I guess, would be along the line. It's of one dimension less. We can take it to be all of Rn, and we could take h of y to be that real simple function there. Incidentally, this is a function that we would say is completely separable because it's a sum of terms. Each term depends on only one of the components of the y vector, and it's about the simplest kind of nonlinear function you can think of. It's just quadratic. And the 1/2 is put there because, remember, we want to take the gradient of this function, don't we? And eventually to get the chi. And so if there's a 1/2 here, when we're taking the partial derivative, say with respect to yj, the 2 is going to come down and we're just going to get partial derivative of that with respect to any yj is just yj. So that makes it even simpler. Okay. So, and that's why that's a solution to that when y is a critical solution. What problem is it in this case? We can say more precisely. Remember, we can describe this problem in terms of the z vector, because it's the z vector that keeps us in the vector space capital Y. So we could say, we could substitute for the first n components of y, we could simply, that vector is simply what? It's simply the z vector times it's simply the z vector times a. Okay, the first n components of that. And then we're taking that sum of squares, we're essentially taking the inner product of that vector with itself. So there it is right there. It's Z transpose times A times Z transpose times A times its transpose. That takes care of these terms, okay, in terms of the Z. And then remember, we have the minus a y sub n plus 1, and that's going to be what? The inner product of the Z vector with that special column vector minus B. So this comes on here. And so we're actually minimizing in terms of Z being the independent variable, Z varying over all of Rm, this thing here. And of course we know linear algebra says we can manipulate this. Transpose of a product is the product of the transpose in reverse order, and matrix multiplication is associative and all that. So that quadratic form simply comes down to this with that linear form there. And actually that problem is already in the literature, and it's called GMRES. I don't know what that acronym means, but that's what it's called in the literature. And you could use the conjugate gradient method on this, because A times its transpose is always symmetric, right? And in fact, it's positive semi-definite. So this is a positive semi-definite form. But to use the conjugate gradient method, you need it to be positive definite. And that would be true here if what? A has full row rank, I think it is. Yeah, has full row rank. But if you look in the books on GMRES, they seem to say, no, don't do that, because if there's a lot of sparsity in A, when you take a sparse matrix and multiply it into its transpose, typically it's not a sparse matrix. And so they do work with this, but they tend to keep it in that form with A and A transpose in there, or even this form here, okay? Okay, so that is one example that can be viewed as a special case. One more example. Actually, it could be viewed, I don't think they ever think of this problem in the light of duality like I'm doing it. They just come across it by, they say, okay, instead of looking for the solution to A chi equal to B, they let chi be equal to A transpose Z. So they're looking for a solution of a particular type. And then you substitute that in, and you get this kind of problem out. And I'm not even sure that they know about this variational principle here, okay? But anyway, that corresponds to that. Now, incidentally, I could also formulate the conjugate gradient method in this context also, but I didn't see any reason to do that when there's time is limited. Now, here's what I call a counterexample, and this is getting at what you were talking about, Xu Chern. You might say, if a given system A chi equal B has at least one solution chi, can you always get that solution choosing any kind of function for h that you want? And the answer is no. It's not, okay? What we've shown so far is if you have a function that has a critical point and the n plus first partial derivative of h is not 0, then you've got a solution.
Right.
But it doesn't say that every solution can be gotten that way.
Then what kind of the A, what kind of structure of A can guarantee you have that? You can find that reversely. What kind of A? In general, it won't hold, but what type of A can be applied to this?
Actually, let me rephrase your question. What type of h?
H.
And we're going to see there's certain h's that will get all solutions, chi, if there are any. And if there aren't any, the optimization problem is unbounded, which sort of fits in with duality and linear programming that. And we'll get to that. That's right. So here, this example here just says take D to be all of Rn. That's bold D, all of Rn. So unbold D would be all of Rn plus 1. And take that bold part just a constant. Remember, the last part is y sub n plus 1. So it's a constant. Our function h now looks like any old constant plus y sub h y sub n plus 1. And the observation here is that if we then take remember we can take the systems independent, the linear system independent of the function h. If I take a system, a linear system that has a non-zero solution, chi, I mean most systems do, right? I can't get it with that constant function. And you can see that because the gradient of a constant is 0. And remember, it's that gradient that's going to turn out to be the solution, and we have a system that has a non-zero solution. Okay, so we have to be careful about how we choose this function h. And the best way, I think, at the moment of deciding how to do that, we're going to do it in a way that no matter how many solutions there are to this, we're going to choose a function h in its domain D so that we'll get them all. Can't miss any of them, okay? And the best way of describing how to do that, I mean, there might be other ways of doing this also, but the one that gets into duality theory is to use the conjugate transformation. And we're going to do this on what I call the expanded version of that. So this, remember, is different from that. You can just barely see the difference here. This involves all n plus variables. This just involves the first n variables. So we're going to go back to that, and we're going to take the conjugate transform of a function, okay? Those of you who don't know about conjugate transforms, you may know about Legendre transforms. And Legendre transforms are very similar. Maybe I'll put that up here. Or maybe I shouldn't. Is there anybody who doesn't know about conjugate transforms? Okay, this will maybe, there's a precise definition there. It simply says this: if we're taking the conjugate transform of a function h whose domain is D, that's what we're doing at the moment, we take the inner product of x with y. X is now going to be the independent variable in the domain of the conjugate transform of hd. Take the inner product of x with y minus h of y, and we soup it as y varies over the domain D of the function h. And we look for those vectors x that make that soup finite, less than plus infinity. For each such x, we put that in the domain C of what's called the conjugate transform function. So, and for each such x in C, namely for which that soup is finite, the value of the conjugate transform function g of x is just that finite soup. That's how conjugate transform is defined. It is a generalization of the Legendre transform. I think I'm maybe running out of time, so let me not go into detail, but I'll sort of point out why that is. If you're souping this, and the soup is actually a max, and the function that you're taking the conjugate transform of h is differentiable, has a gradient, then the necessary condition, say, is that the gradient of that objective function with respect to the independent variable y is 0. So if you write that down, the gradient, that's a linear function with fixed coefficient x. So taking the gradient of that is just x itself minus the gradient of h at y must be 0. So it says that the x here must actually be the gradient of that function h at some y. And so you stick that back in here, you put that back in here, and you get the usual formula for the Legendre transform. So Legendre, 19th century mathematician, he only dealt with differentiable functions. And even with differentiable functions, you want to do this soup here, because the domain of the conjugate transform is typically bigger than the domain of the Legendre transform. And sometimes those extra points that are in that domain are important. Otherwise, you don't get an optimal solution when there should be one. But this is due to Fenchel in the late 40s, and it's very important now. All theories of duality, if they're done in the best way, involve the conjugate transformation in one way or another, and that's particularly true of geometric programming. So we're going to do that, and we're going to come up now with another function. In addition to the function h with domain D, we're going to have a function g with domain capital C. Okay? And so what do we do with that? Counterexample 2. I don't know why that's counterexample there. I'll just read these statements. G, C, and HD they're called conjugate functions, and those of you who know about this already know it, is that if H is a closed convex function, not only convex, but closed, all closed means is it's lower semi-continuous, or a better way of looking at it, the set of all points on or above the graph of the function, that set is a closed set, that's called the epigraph. You can make any convex function into a closed convex function very easily by defining it appropriately at points on the boundary of its domain. And so that's no big restriction. So dealing with closed convex functions is essentially dealing with convex functions. But if you start out with a closed convex function for h, in fact, any function for h, its conjugate transform is always a closed convex function. And then if you take the conjugate transform of that conjugate transform, you get back actually to the original function h, as long as the original function h is closed and convex. So there's a beautiful symmetry there, and that's why the word conjugate is appropriate. It's not true, incidentally, for a Legendre transform. It's not true there. Because things were missing from the Legendre formulation. Okay. Now, here's what incidentally, you can see that symmetry here. If you look at the defining equation for G in terms of H, remember what G is. It's the soup of that expression minus H. If you take any particular X in C and Y in D, then that expression that you're souping has to be less than or equal to G of X. That's just this inequality here. Transpose that over to the left. No, I'm sorry, I guess I want it to the right. Well, whatever, it's the same. That defining formula in terms of soups implies this, and you see the symmetry here. Inner product of X with Y less than or equal to G of X plus H of Y for any X in C, any Y in D. And I might point out right at this point here, this is the basis for duality theory in geometric programming, because our primal and dual problems now, X, remember, is living in a vector space capital X. Y is living in the orthogonal complement of that capital X. Since they're orthogonal, that inner product is 0. If in addition to X being in C, it's also in capital X, X intersects C, and Y, in addition to just being in D, is in capital Y intersect D, then that inner product is 0. And if we say the primal problem is minimize G of X for X varying over the intersect of C with capital X, and the dual problem is minimize H of Y for Y varying over the intersect of D with capital Y, this says the sum of those two feasible objective values is always greater than or equal to 0. That's what some people call the duality inequality. And of course, if you happen to get a pair of a primal feasible solution X and a dual feasible solution Y that makes that equal to 0, then they must be optimal solutions. That's the weak duality theory for this simplest case of geometric programming. Say it's the simplest case because we don't have any nonlinear constraints in there. So that's where we're headed. But now, remember, we've already decided that we want to take the, on the H side, we want D to be such that it is, its n plus first component has to be 1, okay? And No, I'm sorry. It's n plus first component is y sub n plus 1. When we take the conjugate transforms of such functions, over here on the primal side, that puts a 1 there. If you take the conjugate transform of just y sub n plus 1, so simple, to give it to a high school student, its domain is 1, okay? And then it's 0 there. So we want that to be there, and then we want to put all of Rn here. In other words, we want to only choose functions hd whose bold part has a conjugate transform that is all of Rn. Now that's sufficient, it's not necessary, okay? But if it does, it'll guarantee that when we do this, we get the solutions if they exist, the chi solutions. They produce every solution chi to every ax minus b equal to 0, no matter what the system is. That's the only real condition we need. And so this is given on the primal side, but you can also give a similar condition over on the h function, okay? But I don't want to get into all the technicalities of this. How am I doing time-wise?
Yeah, 5 minutes.
5 minutes? Okay. So we choose D to be that, and this is that same example we did before, and we put that there, and GMRES approach produces every solution chi to every system there. That's a proof. I don't know if they knew that, the people who work with GMRES, but whether they do or not, I guess I'll eventually find out. They may tell me, oh, this is not new. But since infinitely many choices of HD for which that relation is true, there are infinitely many dual variational principles that can be used to solve that system and get all solutions. And so that's, now you're going to ask me, Shuchern probably sees in his head why it's okay for that, but I'm not going to try to explain that, okay? That's a fairly deep theorem. But it's a corollary to one of the major theorems in duality theory for generalized geometric programming. Oh, this is the one where I mentioned earlier, when you get that fundamental conjugate inequality, it becomes the duality inequality when you keep x in capital X and y in capital Y, as well as in their domains. So
I think they're telling us that it's almost time here.
okay, I'll end this up real fast. But anyway, where do the linear inequalities come in here? The linear inequalities come in because when you're taking, instead of having, say, lowercase a times an x equal to bi, that's an equation in the original system, a times chi, I'm sorry. You could say greater than or equal to bi, that brings that in. And then the homogeneous form, it's greater than or equal to 0. And then, so you're dealing with a half space in the n plus 1 space. And you can have a mixture of equations and inequalities of that type, all homogeneous. That's a polyhedral cone. Now on the dual side, you're taking linear combinations still with that same special matrix A minus B. Taking linear combination, wherever you want an inequality on the primal side, you have to keep the corresponding zj to be greater than or equal to 0. So now you're taking a linear combination of the rows of that special matrix with some of the coefficients zj restricted to be non-negative. They're restricted to be non-negative when it's actually an inequality on the primal side. Those are dual polyhedral cones, or dual finitely generated cones. You can think of them either way. And they have all the nice properties, almost all the nice properties that orthogonal complementary vector spaces have. Orthogonal complementary vector spaces are just a special case there. And this whole theory goes through. For example, right here, remember there was an inner product of x with y there? Now, since capital X and capital Y are no longer orthogonal complementary, they do have the property, being dual cones, that the inner product of a vector x in one with a vector y in the other is always greater than or equal to 0. So you still get that greater than or equal to 0. Now you have complementary slackness conditions in there, a little more complicated. So you do the same thing with a mixture of linear equations and inequalities. Once you're there, linear programming comes in, because you take primal and dual pair of linear programming problems, you can characterize the solution as a pair of primal optimal and dual optimal solution. They must be what? Primal feasible and dual feasible. Those are linear equations and inequalities. And then the other condition is you take the difference of the two linear functions, keep it less than or equal to a non-negative epsilon. Remember, in linear programming, the primal objective is always greater than or equal to the dual. So you simply demand that they get close enough together with an epsilon. That's an inequality. You can describe all solutions to linear programming problems as finding a solution to a system of linear equations and inequalities. With that, you can do that. So it opens up a whole new range of possible algorithms there. I don't know if any of these will do anything, okay? I don't know about that, but anybody wants to find out, and you do any experimentation with any of these kinds of functions, let me know. I'd appreciate hearing about it. So, I have 1 minute for questions.
Yes, let's first thank our speaker.
Appreciate you coming.
We have time just for a couple of questions. Unfortunately, any questions?
There's no question. Can I ask enough? But if there's no one to use the time, let me ask you one thing. Okay. Now, supposedly we take that ax equal to b originally, right? And then supposedly I say that I just add a constant objective function as a linear program, solving system of linear equations, the same as solving linear programming problem. Am I right?
I guess so.
So we have that, right?
I'm not going to argue with him because he's written books on linear programming.
So we are doing it, and then say that interior point method can be fast to solve that, right? Now the interior point method definitely somewhat involved. Still have the problem of AA transpose. The same will be the same as that
GMRS or something.
Okay, the same is AA transpose is going to destroy the structure of the sparsity.
Mhm.
So the linear now beginning you were saying that this will be faster than be better than this interior point method. I meant to ask that.
Oh, I'm not saying it will be. I said
I'm
it
just saying,
might be competitive.
No. Now I see that if you directly using the linear programming approach to solve it using the interior, then you are going to have the same problem as that the GMRS, IES, or whatever. This have AA transpose that thing. Okay, AA transpose destroy that the structure of the sparsity.
Yeah.
And here you are providing some more of the more general platform. But the real problem, so that they could potentially avoid having that AA transpose things were not there.
I think that's right.
Because when you are looking at the dual problems, okay, that structure of AA transpose is not necessary to be there.
I don't think so.
It's not necessary to be there. But
Unless
the
you can
dual, you
prove
have
it's
A
there, then
transpose.
it's
No,
there.
the dual, you may still have that A transpose something somewhere.
It
All
might
right.
be.
It might be somewhere there, they reappear. Okay. Now, real question here is that, okay, how am I going to get what type of this H and the D? Okay, I'll be able to really not using the structure of AA transpose, but solve it nicely. I think that.
I'm glad you brought that up.
Yeah, that's it.
Because I didn't think of it. I don't know enough about interior point methodology that I realize that AA transpose
A
is
transpose is in the primal problem. AX is a square A transpose. In the dual problem, AS minus 2 A transpose. It's in the primal dual AX S A transpose. They all have the same structure. Okay.
Well, there's a good problem to where it's a theoretical problem. Is there a choice for HD?
Such that you
You
don't have
avoid
to
that.
end up being trapped there. If you are able to do that, then you can say that this is a much nicer thing, can retain this sparsity structure, and I'm solving the problem.
And
That might be interesting.
that's, if you work on that, let me know. But a related question is, how does that interior point methodology, can it be viewed as a special case of this? Or I don't know, maybe this is a special case of that. I don't know exactly how it relates
Well, for
yet.
that, I was solving, remember that I had student Seiwei Chen, we're trying to solve this AX less than or equal to B with something structure that, and then we blankly add this entropy function on top as an objective function. But then X have to be modified in a way that is well defined. Then we look at the dual, pretty much in the m-dimensional, which is unconstrained.
And when you take the dual there, you're taking a conjugate transform.
Conjugate transformation, conjugate dual of that particular one.
Right.
And then coming back, you still have Z, and then work on that the dual. You will have an log X log. You will have exponential of. Basically, that will be the sum of that is A transpose of something. We were trying to do that.
I see.
So,
Well, it would be nice to know how all of that fits with
Yeah.
this. I think there are a lot of questions here, and anybody who wants to work on
but
this.
then I was unknowingly doing that without really look at the whole structure of this. Now I see that actually we have a much broader test that might be able to do. So we compare that with the Mansarin's and the Ketamurti's work. They have done some AX equal to B and the AX less than or equal to B. They did some numerical method to do it. And then we show that it's more stable and then able to, if we stop at the early time, we will have a much better solution than theirs and so on and so forth. But without really look at the whole structure of this. Now I get some more new ideas on this.
Great.
Thank you.
Yeah, my only goal in this is I don't know the answer to all these questions, but I hope anybody who's interested will look at special cases and and see what all this is.
Just a very quick comment, though. At least from an application viewpoint, this is actually quite an important problem in spectral analysis in general, in array processing and things like that, where people typically. But you do have some structure in the A matrix.
Right.
They have like a Vandermonde structure or something like that, and people go like the eigenanalysis type of approach and things like where you're searching for these two orthogonal spaces, subspaces, and so this is very important. Actually, very important.
So all of that might be.
Oh yeah.
Taking advantage of the structure of A, may be able to construct a particular type of edge.
Yes.
That's what I'm
This
hoping
is what
for.
I was asking previous one of the question. What corresponded? Yeah.
That's what I would hope for in all of this, that you have so much flexibility here with that H function, infinite flexibility, uncountable flexibility, that you might be able to exploit various kinds of sparsity and so forth. But I don't know how to do that. All I'm saying is here's a structure to think.
In a practical setting, the structure is imposed basically by the physical layout of your sensors and all that stuff.
Yeah, maybe H should be something like an energy or something like that. You know what I mean? In a certain physical context or something.
Well, you can have a lot of different interpretations.
That's right. But what this is saying is there's a lot of flexibility here. There's no flexibility like that in the conjugate gradient methodology.
Well, let's thank the speaker once again.
Appreciate all the questions.